Section 8.5, Vectors and Applications. Now the next two sections, 8.5 and 8.6, are both going to deal with vectors. This section, a little bit more the basics of vectors, and then the next section we'll get into a little more complex concepts dealing with vectors. But vectors have a lot of real-world applications. They're very useful in physics when you're talking about motion of an object or direction of an object, forces applied to objects, this type of thing. So there's a lot of applications in physics, and of course math is involved with that. That can be used or can be represented using this idea of vectors. But before we get into the calculations involved, now of course you're going to see a lot of the same calculations we've been using before. I tell you those are going to keep coming up. It's just a different context. Right? So in the context of vectors in this case. So first, some terminology to be familiar with. The difference between a scalar quantity and a vector quantity. A scalar quantity is a quantity that has what we call magnitude. It's simply a value or quantity that has measurement, right? So like time you measure in seconds, length can be measured in feet, mass of an object may be measured in kilograms, right? So that's the magnitude of those quantities, right? So the measurement. As opposed to a vector quantity, which has magnitude, but also has direction. So what we call like displacement. An object moves a certain distance in a certain direction, right? Velocity. An object travels at a certain speed in a certain direction, right? We tend to think of speed and velocity as the same thing. Not exactly, right? Speed would be something like maybe I'm traveling at 60 miles per hour. That's my speed. Throw a direction component to that. Say, okay, we're traveling 60 miles per hour west. That would be our velocity, right? So there's also a direction involved. Force, as I mentioned earlier, there's a lot of applications with vectors of force, where you have a push or a pull that's being exerted on an object in a certain direction, right? But the common theme there is we're throwing in direction when we're talking about a vector. So it's a quantity that has magnitude, right? Some measurement, but it also has a direction component. Graphically, vectors can be represented using directed line segments. We talked a little bit in that last section about that use of the term directed. So a vector is a line segment, and the length of the line segment is its magnitude. But then it's a directed line segment, so of course it has a direction indicating the direction in which the object is moving or which the force is being applied or that type of thing. Two vectors are equivalent if they have the same magnitude and direction. Now that may seem pretty obvious, to say that two vectors, what does it mean to say that two vectors are equivalent? Well, they have the same magnitude, they have the same direction. Now, when you're drawing a vector, graphically representing a vector, the thing to keep in mind is the length of the segment that you draw is the magnitude. So the length is going to represent the quantity or the measurement of the quantity itself. And then we place an arrow on the vector to indicate the direction, right? Not to indicate that that segment continues like you do with rays and lines, but simply to show the direction. So like in the diagram that I have at the bottom, the graph, if we consider a vector drawn from point A to point B, that point A is called the initial point of our vector, and that point B is called the terminal point of a vector. So every vector is going to have an initial point and a terminal point. And then notice there's an arrow at B. That is not to say that we're continuing in that direction. That is simply used to show the direction of the vector. So as opposed to putting the arrow on the opposite side, which would be vector BA. Right? So we always name the vector with the initial point first and the terminal point second, because that would indicate our direction. So vector AB and vector BA would be two different vectors. Right? They're the same vector, but in the opposite direction, right? And which makes them different vectors. Symbolic notation, right? So vector AB, using that little notation that I have here with the little arrow or the ray looking thing symbol above the AB. Now again, it's always in order from initial point to terminal point. We also quite often you'll see bold-faced type used or bold-faced letters. When you're looking at it in a textbook, you'll see bold-faced AB. Or, as I have here, oftentimes you see vectors named with letters like U, V, W, right? So vector U, vector V, vector W. One other thing just to mention, and this is for your future reference, and my neighbor decides to cut his grass right now, but the initial point and the terminal point of your vector, they're also called the head and the tail of the vector. This textbook doesn't use that terminology, but for future reference, that point B is called the head, and that point A is called the tail. All right, so the head has to go before the tail, so in the direction of the vector, B would be the head, and A would be the tail. Right, but we're going to call it initial point and terminal point. That's the terminology that's used in this text. Now, the 4 vectors that I have drawn in that diagram, those are all equivalent vectors. They all have the same magnitude or length, and they're all in the same direction. So that's to keep in mind. When we say direction here, we're talking about the same general direction, right? So vector AB, vector CD, vector OP, and vector V are all equivalent vectors. And again, for future reference, the one that we're most interested in, or that we would usually make use of, would be this guy, would be that vector OP, because I can use vector OP to represent any of those vectors that are equivalent to it. And since OP has its initial point at the origin, it just makes it a little bit easier to work with. Right, so we'll talk more about that later, but representations of vectors. But for now, all those vectors are equivalent to each other. They all have the same magnitude, and they all have the same direction. Now, equivalent vectors. How do I show that 2 vectors are equivalent to each other? Right? Well, since they have the same magnitude or they have the same length, we can calculate the distance from the initial point to the terminal point using distance formula. Right? So we'll go back to some basic algebra. We have the distance formula for finding the distance between 2 points. Call them x1, y1. I'm just going to use that notation. So our initial point we're going to label as x sub 1, y sub 1. Our terminal point we'll label as x sub 2, y sub 2. And so the magnitude of the vector can be found using our distance formula between those 2 points, x sub 1, y sub 1, and x sub 2, y sub 2. Now, remember the distance formula. And that just comes again from Pythagorean's theorem ultimately. But the distance between 2 points in the plane, point A and point B in this case, the difference in their x coordinates squared plus the difference in their y coordinates squared. So you may need to remember your distance formula, review that. Also notice this notation. I have another notation that we use for the magnitude of a vector using absolute value, because if you remember, what does absolute value measure? It measures distance from the origin or distance from the pole, right, depending on our context. Here it's distance from point A to point B. So using absolute value to represent the magnitude of our vector. And so you will see that notation used. You also see this notation used, right? So either one, but I'm going to use that absolute value notation to show magnitude. All right, so that's the length of the vector. So we check the magnitudes, distance between initial point, terminal point. Are those the same? If so, okay, we have the same magnitude. How do we check the direction? Well, if we have vectors that have the same direction, since these are line segments, then they would have to have the same slope. All right, they'd have to have the same rise over run, general direction, to show that the vector has the same quote-unquote direction. So we just simply calculate the slope of each of the vectors, of each of the line segments, using our basic slope formula, right? Change in y over change in x, so y2 minus y1 over x2 minus x1. Also keep in mind, and even in the diagram that I just showed you, there are 4 vectors that are equivalent to each other. I could draw any number of vectors there that are equivalent to each other. All right. So ultimately, there are an infinite number of vectors that you can draw or that you can give that are equivalent to any given vector. All right. So we can move these things all over the place in the coordinate plane. Just keep that in mind. For example, right, so I mean, this is not, there's nothing really tricky here. It's just going to rely upon our basic use of algebra with the distance formula, with our slope formula. That's all really this is. So for example, first I'm going to sketch the vectors in the coordinate plane. And we want to determine if each pair is equivalent, right? So is vector, or are vectors u and v equivalent, or vectors w and p equivalent? So I'm given in the table vector u, v, w, and p. I've got the initial and terminal point of each vector. And so drawing the vectors in the coordinate system, or in the coordinate plane, is nothing more than plotting those points, right? So here's vector u, initial point, terminal point. Here's vector v, initial point, and terminal point, right? And then, we draw the line segment, and then we place the arrow on the terminal point to show the direction of the vector. And so there's two components to our vector, its magnitude and its direction. So then if I want to show or try to determine if those two vectors are equivalent, now of course, if you're drawing this stuff by hand, don't always rely exactly on your visual. If you're artistically challenged like a lot of us are, your diagrams may not be exact and you can mislead yourself visually. So we'll do the calculation. We'll find the magnitude of vector u. Now again, that's just nothing more than distance formula. Plugging in our initial and terminal points. So I've got the change in the x coordinates, -2 minus -4 or +4 squared, plus the change in the y coordinates, -1 minus 3 squared. And just plug that into our distance formula. That'll give us the square root of 4 plus 16, or square root of 20. And that's the magnitude. Now I could simplify that if I wish, but it doesn't serve any purpose here. All I want to show is, do these two vectors have the same magnitude or not? So whether you write that as 2 square roots of 5 or square root of 20, that's fine. Remember our objective. What's the direction of vector u? Find its slope, right? We can tell visually, though, at least we know the slope there should be negative, because we have a segment that's decreasing from left to right. But we'll just plug that again into our slope formula. Change in y over change in x between our initial and terminal point. So change in y, -1 minus 3. Change in x, -2 minus -4 or +4. So I've got -4 over 2 or -2. And there's the slope of that vector. Vector v. Again, just using distance formula. Initial point is at 1, 1. Terminal point, 3, -3. So I'll take the difference in the x coordinates, 3 minus 1 squared, plus the difference in my y coordinates, -3 minus 1 squared. And I've got 2 square root of 4. I've got -4 square root of 16. So again, I get square root of 4 plus 16, or square root of 20. So I've got the same magnitude of vector v that I do for vector u. And then we check the slope. Again, change in y over change in x from initial to terminal point. -3 minus 1 for our change in y, y2 minus y1. And 3 minus 1 for our x, x2 minus x1. And I've got, again, -4 over 2 or -2. So vectors u and v have the same magnitude. They both have a magnitude of square root of 20. And they both have the same, or in the same direction, because their slopes are the same, -2 in both cases. So I could then say that vectors u and v are equivalent vectors. Vector p and vector w, I went ahead and graphed those. Vector p had initial point at 0, 2, terminal point at 1, 4. Vector w had its initial point at the origin, 0, 0, had a terminal point at 2, 4. Now those two vectors, you can visually, we're good enough with our drawing, we can visually inspect and see that those are not equivalent vectors. They look to have the same direction, and we could check the slope of those to verify that, but they obviously do not have the same magnitude. Vector w is much longer than vector p. You can check that, of course, use your distance formula there, but obviously those have different magnitudes. So vector p and vector w are not equivalent vectors. They do have the same direction, it turns out, but they do not have the same magnitude. Okay? So that's how you determine if two vectors are equivalent. Always wants to throw me back to the top. Here's really the biggest part of this discussion, vector addition. All right, so general notation and terminology for vectors. Now vector addition, because this is what comes up in your application type situations, where we are applying multiple vectors and looking for a net result. All right, what's the net outcome or the result of the application of multiple vectors on an object, especially? So there are two different methods or two different ways that we can perform vector addition. There's this triangle method, and then there's also this parallelogram method, or parallelogram law, as I have it noted there. The triangle method kind of explains exactly what's maybe a little clearer as far as what's going on in terms of determining the resultant, or what we call the resultant vector. The parallelogram method is actually the one that we typically use to do the calculations. Right? So we'll start with the triangle method, and then I'll talk about the parallelogram method or parallelogram law in detail. So with the triangle method, we have an object that travels a certain distance in a given direction. And so we can represent that with our vector u. Right? So we're starting at point A. Our object travels along vector u to point B. All right, so we have a certain distance in a certain direction. Then our object changes direction and travels a certain distance along vector v. Right? So from point B, it changes direction and then travels up to point C. So there's vector v, distance and direction. When my object ends up at point C, I can look at this vector from A to C, or we could call that vector AC, as what we call the resultant vector. And that one vector represents the net result of the application of both vectors u and v. So we refer to it as the sum of vectors u and v. Right? So we have a total displacement, which would be the magnitude of vector u plus v. We call it again the resultant vector. And in applications, this is the vector that we're interested in, right? We want to know what is the resultant, what is the outcome of the combined application of our two vectors in this case. Of course, you could have more than two, but we're just going to limit it to two for now. Here's the parallelogram law or parallelogram method. Now I said this is the one that we typically use when we're actually doing calculations. So we can also describe vector addition if we take the initial points of our two vectors and place them at the same point. Then we're going to complete a parallelogram and find the diagonal of the parallelogram. So in other words, what we're doing is, and notice if and kind of look at the diagram that we have, here's the same vector u that we had initially in the previous triangle method, right? And then we turned and we applied vector v, and then u plus v was our resultant vector. Notice all we're doing is we're taking this vector v and we're sliding its initial point down here. So that vector u is still here. And then vector v just got slid down vector u to where they match, or they have the same initial point. And then there's our vector v. And then what we're doing is we're forming a parallelogram, which notice opposite sides of the parallelogram, vector v and vector v, vector u and vector u. We form that parallelogram, and then the diagonal of the parallelogram is your resultant vector. There's your u plus v. So it's the same vector regardless of whether you have the triangle method or this parallelogram method. The parallelogram method typically makes it easier to work with in the context of an application because it would place the initial point at the same location. We can then, it just makes it easier to find this guy. All right. And so again, not a whole lot of song and dance there. That's typically the more useful application or process Right? Not that triangle method can't be used, but it's parallelogram method that typically makes it easier to work with the components of your vector. Okay? Also notice something else. Vector addition is commutative, which remember commutative means you can add things in opposite direction and get the same result. So u plus v, v plus u. Because notice, if I start here and I travel along vector u, and then I change direction and travel along vector v, that would be vector u plus v. Let's say instead I start at this point and travel along vector v, and then change direction and travel along vector u. Right? I end up at the same location, but that would be representing vector v plus u. So u plus v, v plus u, gives you the same resultant vector. So vector addition is, we say, commutative. But that's the process that we tend to use application-wise. It tends to fit better into application situations. So a few examples. And I'm going to keep these fairly basic, because I know this is difficult to try to learn all this stuff on your own, basically, as you're doing. So I'm going to try to keep these fairly basic in their applications. So let's say that I have two forces, call it F1 and F2, that act on an object. The combined effect of those two forces is the sum or the resultant of those two forces, so F1 plus F2, of those separate forces. All right, so this is kind of, like I said, a good physics application where, let's say I've got an object and someone is pushing on this object from this direction, someone is pushing on the object from that direction. All right. So which direction, or what happens to the object? How does it move? Right, well, they're each applying a force, whether they're applying the same force or different forces. The object is going to travel in this direction. Right? We're going to have an application of the two forces, and the net result is going to push the object this way. Right? Unless one person just simply overpowers the other person and knocks them out of the process. Right? But this is the general idea. If you apply different forces at different directions, there's going to be a net result of that. Right? What happens to your object if you apply forces at different directions? Okay? So that's what we're exploring here. So in this case, for this example, we have two forces, one of 50 newtons and one of 60 newtons. So that'll give you an idea of one of your units of force, the newton. So we have a force of 50 newtons and 60 newtons, two forces acting on an object at right angles. All right, so as I have in that little diagram, we're going to apply the forces at right angles to each other. We're asked to find the magnitude of the resultant and the angle that it makes with the larger force. All right. So our diagram, similar to the one that I have drawn there. Here's our force, 60 newtons in this direction. Here's our force of 50 newtons in this direction. All right, now notice too, we always talk about with these diagrams when you're trying to represent, and maybe even a little more importantly here, representing these vectors, the length of the vector is its magnitude, which is the measurement of the quantity. Right? So in this case, it's the force that's being applied, 60 newtons versus 50 newtons. I'm drawing that side of the 60 newtons a little bit longer than the side or the vector with magnitude 50 newtons. Right? Now, that helps just to kind of give you a better visual of the diagram. We always talked about that with our diagrams. They don't have to be perfect, but we at least want them reasonably so that when we can kind of visually inspect the situation, we have a decent idea of what's happening. And then when we do our calculations, we can kind of use that to a certain degree to double check to make sure our calculations make sense. So if I come up with a number that really just doesn't look right, I can maybe observe that from my diagram and gives me an idea of what's going on there. So it doesn't have to be. I don't want to draw that 60 newton vector twice as long as our 50 newton vector, because that wouldn't be to scale reasonable. But at least draw it a little bit longer, so that when you form your parallelogram. Now in this case, my parallelogram ends up just being a rectangle. Right? So I'm just taking from those two terminal points and just forming our parallelogram. It's a rectangle in this case because we're told that the angle between our two forces is that they're acting on each other at right angles. So the angle is 90 degrees. Now, I don't have any other information than that, so I just put my 60 Newton angle vector at the bottom, and my 50 Newton vector is the vertical vector. You could reverse that. We're not given any other specific direction. We just know that the angle between the two vectors is 90 degrees. And then once we draw our rectangle, we draw in our diagonal, and that's our resultant vector. That's u plus v. Now, in this case, since we are dealing with a rectangle and then ultimately right triangles, we can fall back on some basic right triangle trig to find our resultant vector. Because if I take one of those two triangles, let's say this one, and I'm looking for then what the hypotenuse of that right triangle, and I'm looking for the angle. We were asked for the angle that it makes with the larger force, which was 60 newtons. I think that was our other part of our question. All right. Find the magnitude. All right, dang it. That's irritating. Find the magnitude of the resultant and the angle that it makes with the larger force. Okay, so that's the angle theta that I have labeled in our diagram. So this one falls back on just basic right triangle because we ended up with a rectangle. So I could find the magnitude. Now remember, that resultant vector u plus v, we want its magnitude, which is its length. So I'm looking for the length of that hypotenuse of that right triangle. And I can do that using Pythagorean's theorem in this case because it is a right triangle. So that's all I used here. So our square root of a squared plus b squared equals c, the length of that vector, the magnitude of u plus v. So I plugged in 50 and 60. I got square root of 50 squared plus 60 squared. And you plug that in, you'll get approximately 78. And our unit there was newtons, right? That was the result of the force. That's the force being applied to our object. So our resulting force would be 78 newtons. And notice, again, just kind of a little observation here. You'll explore this in more detail if you take physics. So notice we have 60 Newton force we have two forces being applied to the object, 60 newtons and 50 newtons. So there's a total of 110 newtons of force being applied to the object. But because those forces are being applied in different directions, the net result of those forces is only 78 newtons, right? Because you're canceling each other out to a certain degree by not applying the forces in the same direction. So you do get an increase in the amount of force applied, right? But that's how that stuff works. So again, take physics. You'll play around with some of this. It can be a little interesting in application of forces. Now, the angle that we make with the larger force, so that's our angle theta, our resultant vector u plus v, and our vector u, 60 newtons. And there again, I'm just using basic right triangle trig. We know the length of the two sides, 50 and 60. Right? So I've got 60 newtons along here, I've got 50 newtons along there, and we're looking for the length, or for that angle, theta. So basic right triangle trig, opposite and adjacent. I know the tangent of theta would be 50 over 60, opposite over adjacent. So the inverse tangent of 50 over 60 is approximately an angle of 39.8 degrees. All right, but again, that's just going back to basic right triangle trig. That's why I said there's really nothing new calculation-wise with anything we're doing. We're just doing it in a different context. So you have to go back and remember all those different things we worked on. The next one is just, again, more of a little generic situation. Let's see, before that, now my dog's going to bark. We've got a lot of nice noises today. This next example, you can skip that one. I want to just kind of keep this fairly basic because I know y'all are having to do a lot of this on your own. So this is a little more of a complex application type problem. Just to mention something in general about this, because again, it is real world application. You have an airplane flying in a direction, say from San Francisco to Honolulu, and we're given the bearing on which that plane is traveling, right? Its direction. We know the speed of the plane, 450 miles per hour. So that gives us our velocity. It's a speed of 450 miles per hour in a direction of 233 degrees. You also have a wind that's blowing at 39 miles per hour from a direction of 114 degrees. So you have a wind or a crosswind that's blowing the airplane. Finding the resulting bearing and ground speed of the plane. So you think about this, and again, I don't want to get too much into this, just want to give you the general idea. You have a plane that's flying in a certain direction or on a certain heading, and then there's a wind that's blowing from the side, pushing the airplane to the left or to the right, depending on which direction the wind is blowing from. That's going to affect the course of the plane, right? Because if they don't adjust their course to account for the wind that's blowing across from the side, that's going to blow them off course, right? So that's the kind of calculations that have to get done. You know, you're flying an airplane, or maybe you're in a boat, and you're trying to take the boat from one side of a lake to the other side, and you have a wind that's blowing you. You know, if you aim for the point directly across the lake that you want to land, you're not going to land at that point because the wind's going to blow you off course. Maybe there's a current if you're in a river, and the river current is going to blow you off course or pull you off course. So you have to adjust for that. Right? So you have to adjust the angle at which you travel so that you can actually land at the point that you intend to land. Right? So that again that's a good place or a good example of how vectors are used. It all comes back to vector applications. So direction and magnitude and all of this for different forces acting upon your object. All right, but again, you can skip this one. I'm going to keep it a little bit simple here. I don't want to get into the weeds too much with this stuff. So here's just kind of a generic example. We're given that the magnitude of vector u is 54, the magnitude of vector v is 43. We're given the angle between vectors u and v to be 150 degrees. We want to find our resultant vector u plus v, giving its magnitude to the nearest tenth, and the angle that it makes with vector u to the nearest degree. All right. So we're given our information, we're given the magnitude of the two vectors, and we're given the angle between the two vectors. So in my diagram, here's vector u, magnitude of 54. Here's vector v, magnitude 43. So I drew vector u a little bit longer than vector v. And then here's the angle 150 degrees between the two. Now notice, again, all we know is the angle between the two. We don't have any other orientation, so I just usually draw one horizontally, like I drew vector u horizontally. And then I measure the angle 150 degrees, and we draw vector v. That's usually the best way to do that. It's the easiest way to do that. All right, forming our parallelogram. Right, so once I have our two vectors drawn, so we form our parallelogram, and then we have our resultant vector. There's u plus v, the diagonal of the parallelogram. Now we know the opposite sides of the parallelogram are equivalent, right? So if vector u is 54, then this side of the parallelogram has to also have a length of 54. If vector v is 43, then this side of the parallelogram also has to have a length of 43. There's something else that we know. We know the measures of the angles of a parallelogram are actually the measures of the angles of any quadrilateral. They have a total of 360 degrees. You know, we always talk about triangles have a sum of 180 degrees. Parallelograms have a sum of 360 degrees. You could justify that two different ways. If we go back up to this rectangle, right, each of the four angles of our rectangle is 90 degrees, so 90 times 4 gives me 360 degrees. You could also look at it in terms of the triangles, right? These quadrilaterals, the rectangle or the parallelogram I have here, there's two triangles in there. And if I add the angles of each of those triangles, I get 180 degrees. And those two triangles then together would give us a total of 360 degrees. So either way you look at it, that is one additional piece of information. A quadrilateral, the sum of the four angles, is always 360 degrees. We also know that the opposite angles in the quadrilateral, in the parallelogram in this case, have to have the same measure. And that goes back to the fact that the sides have the same length, opposite sides, so opposite angles have to have the same measure, right? So if this angle, some of this, if this angle try this again. So if that angle measures 150 degrees, then so does this angle. All right. And so between those two, you have 300 degrees. Now we know there's a total of 360 for the parallelogram, so that leaves 60 degrees between the other two angles. So we'll just divide that by 2, and that'll give each of these angles a measure of 30 degrees. So that's where the 30 degrees comes from. The fact that the sum of the angles is 360. I've got those two 150 degree angles, which eats up 300 degrees. I'm left with 60. Divide by 2 to get the measure of each of those other angles. Now, once you have that angle, we're good to go. Because now, all I'm looking at is this triangle, or you could take the other one, either one. I know the length of this side. I know the length of this side. And I know this angle. What am I asked to find? That resultant vector u plus v, which is the third side of your triangle. And we want the angle between that vector and vector u, which is what I have labeled as angle theta. So I went ahead and pulled that triangle out, as we're apt to do when we're dealing with these applications. So here's vector u, here's vector v, and here's our resultant vector. So I have those labeled as angles A, B, and C, sides A, B, and C. There's our angle of 30 degrees. So what do I know? I know two sides and the included angle. That's an SAS triangle. Right now we're just back to basic solving of triangles or finding missing pieces. And with the SAS triangle, if I'm looking for that third side, that is a use or application of law of cosines. Now, again, the length of the side is the magnitude of the vector. So the vector is u plus v. The length of that vector is its magnitude. So that's why I'm using that notation. So the magnitude of u plus v, the length of that third side, and this is just, again, law of cosines. So it's the square root of the sum of the squares of the other two sides minus twice their product, and the cosine of the included angle. All right. So we plug that in, and you should get approximately 27.3 to the nearest tenth. So that would be the length or magnitude of that third side of the triangle. It's the magnitude of our vector, our resultant vector u plus v. And then once you find that value, now I've got angle C at 30 degrees. The length of side C is 27.3. I'm looking for the measure of angle A. We know the length of side A, 43. Well, now I can use law of sines to find angle A, because now I've got angle C and side C opposite each other. And then using the length of side A, setting up our other ratio with sine of angle A. Right, so this is all that law of sines, law of cosine stuff that we looked at back in sections 8.1 and 8.2. So there's our law of sines, sine C over C, sine A over A. Solving that for sine A, I get sine A at approximately 0.7875. And our inverse sine of 0.7875 gives us an angle of approximately 52 degrees. So that would be our angle theta, angle A, which is the angle between our resultant and vector u. Last piece of this is going to take it in the opposite direction. Right, so previously we were given our two vectors and we were asked to find the resultant. What if we have the resultant and we're asked to find these vectors u and v, which we're calling u and v here the components of our resultant vector. So given a resultant vector, in this case we're calling it w, how do we find vectors u and v, whose sum is w, right? So w is a resultant of u and v. Now u and v are called the components of vector w, because notice u and v, those are perpendicular to each other. We refer to these as the horizontal and vertical components of your vector W. I mean, because there's other combinations of vectors that would give you vector W. Those are not unique, but they are the horizontal and vertical components. Right? So if we have those vectors acting upon each other at right angles, what is the resultant? So we call this resolving a vector or representing a vector, where we're finding its components. Right? So resolving a vector or decomposing is the other term we use there as well. But resolving a vector or representing a vector. So it's taking a vector and breaking it back into its vertical and horizontal components. Right? And again, it's really just going to go back to right triangle trig. Right? So once we set up the right triangle, right, if I know the magnitude of that vector u, vector w, get this out of my way, that's the length of the hypotenuse of that triangle. Right? And if we know one of our angles, then I can use our basic right triangle trig to find the lengths of the two sides, right, using basic right triangle definitions of our trig functions. So for example, I've got a vector u, magnitude of 150 pounds, which is inclined to the right and upward 52 degrees from the horizontal. Resolve the vector into its components. So there's our vector with magnitude 150 pounds, which is inclined to the right and upwards 52 degrees from the horizontal. And to resolve the vector, to find its components, all we'll do is form our right triangle. We have our horizontal and vertical components. Horizontal component, call it X if you wish. Vertical component, call it Y. But this is just basic right triangle trig. The horizontal component, we've got that the cosine of that angle, 52 degrees, would be x over 150, or x equals 150 times the cosine of 52. And that should look familiar. That's the same calculation that keeps coming up with all this stuff. When we were doing complex numbers, when we were doing polar coordinates, right? That horizontal distance is r cosine theta. And the vertical distance is r sine theta. Right? But it's all based upon the basic right triangle trig. So however you want to get there. But I've got cosine of 52 is x over 150. So x is 150 times the cosine of 52, which gives you approximately 92.3. Our units there was pounds. That was the magnitude of our resultant, 150 pounds. So our components are also going to carry the same units. And then for our vertical component, we've got the sine of 52, which would be y over 150, right? Opposite over hypotenuse. So y then is 150 sine of 52. That should be 52, not 152. I think I meant to put a parentheses there, probably. Okay. And that would give you approximately 118.2, and again in pounds. Right? So that's resolving a vector. That's pretty straightforward business, but again, I guess it's just about the language, so when they ask you to resolve a vector or represent a vector, what do they mean? Right? We're finding the horizontal and vertical components. We're simply setting up a right triangle using basic right triangle trig to find the lengths of those two sides. Right? And that is it for section 8.5.